everybody, I'm Chris Brightwell from Humiseal Europe, part of Chase Corporation. And what we're introducing today is our new range of coatings called SEC coatings. And this range, they address an issue with current coatings that are on the market that isn't addressed elsewhere. SEC stands for sharp edge coverage. And an issue with current coatings is that they coat the tops of components nicely, they coat the flat surfaces of circuit boards nicely, but corners and vertical edges, the coverage is often less adequate. This can lead to leakage current and failures in condensing environments or if the boards are immersed in water. So what we're going to demonstrate today is how these SEC coatings work and just how effective they are. This is a test board that we are using, a range of component types on it, ceramic capacitors, resistors and QFP silicon chips. Each component is either charged to 24 volts or 0 volts. So this one is 24 volts, 0 volts, 24 volts, 0 volts. And we're going to see if we immerse this board in liquid or condensation and each component does not have adequate coverage, you're going to see leakage current between it. So this is a board that has been coated by our new coating 1B59 SEC. It's been applied with an atomized spray process, and I think you can see here that the coverage is very uniform. You can't see any lack of sharp edge coverage. You're going to need to do cross-sectional analysis to prove this, but I will demonstrate that it has sharp edge coverage but with a simple test. So what we've got here, we've got a way of demonstrating leakage current in a highly forceful situation. We're going to take circuit boards like the one I've shown, and we're going to first immerse them into tap water and look for leakage current, and then we're going to immerse them into salt water. And the higher the leakage current, the less adequate the coverage is, and consequently the more likely the board would be to fail in a real world situation if the board was exposed to either high amounts of condensation or water immersion. So I'm going to start first with with a non-ideal situation with a board which has got no coating on at all. So I can show that this is like the board I showed you, but there's no blue fluorescent glow. This has got no coating on. So this is worst case. And the first thing we're going to do, we're going to plug it into a power supply, which is going to apply 24 volts to each component or no volts to the next component. And we can see here current leakage, and we can see when the board is dry, the current leakage between components is very low. First, I'm going to immerse the board into tap water. And we can see now we've got 0.6 of an amp, 600 milliamps of leakage current. And I don't know if we can see here, but we can see there is enough leakage current that we're actually getting electrolysis on the board, and we can see oxygen and hydrogen being given off. And the situation becomes even more extreme if the water has got a lot of ionic content. So this is water which has had salt added, and we can see here the leakage current. In fact, it's beyond the capability of this power supply. We've got 1.8 amps of leakage current. So that's worst case scenario. I'd hope by now anybody who wants reliability in their electronics is using conformal coatings. Let's move on to what the current situation is with a conformal coating. This is a regular coating that's been applied in one layer in a regular way, and we can see here we've got the blue glow. This has been applied in one layer. This is typical of many boards and many processes that are running currently in the electronics industry. We're going to immerse this into tap water. The situation is nowhere near as dramatic as an uncoated board, but we can still see we've got 140 milliamps of leakage current with a board. This is due to lack of coverage on the corners of components. we immerse this into salt water, and you see here we've nearly got an amp of leakage current, and again we're seeing a significant amount of electrolysis. So what I'm going to show you now is one of our newly developed coatings. As I showed you, this is now our product 1B59 SEC. It's a synthetic rubber coating which has got high temperature performance to 150 degrees C. It's a flexible coating. It's able to withstand expansion and contraction, thermal shock. It puts low stress on the components. Up to now, coatings made from synthetic rubbers have been available, but we've expanded the capability of these products by introducing this SEC concept. So the liquid properties of the coating have been modified. So as well as coating the tops of the components, it coats the corners of the components, and it coats the vertical surfaces of the components. And I'd like to demonstrate the performance of this in the water immersion test. So I'm going to show what I showed with the other two coatings. I'm going to immerse this first into tap water. And we can see no leakage current. I'm going to immerse it next into salt water, and we can see no leakage current. The synthetic rubber coatings are very hydrophobic. They have very low moisture permeability. So you've got the benefit of that and the benefit of perfect sharp edge coverage, which is providing such good performance in this test. So this is Humiseal 1B59 SEC conformal coating. We've got another product which is based on polyurethane chemistry, which is 1A33 SEC. And later this year we will be also promoting UV curable SEC materials. Okay, so that's Chris Brightwell from Humiseal demonstrating the high performance of our new SEC materials.